Hi, I'm Maria. I'm a PhD student at Dartmouth College, and I'm collaborating with Andrew Roof on this tool I named PathQuarry. We're running PathQuarry on public known vulnerable systems that discover vulnerabilities and explore attack chains in cloud environments. So today, cloud environments often have misconfigurations that let attackers pivot between roles, escalate admin privileges, and pivot within account boundaries. These are difficult to identify because individual misconfigurations look benign in isolation, but become dangerous when chained across multiple services within an attack surface. So as a result, the attack surface becomes too large to enumerate by hand. Before I get into the rest of the talk, here's a little background on me. I'm a security researcher and PhD student at Dartmouth College. My research interests are binary analysis and graph theory, among others. And here are some social media handles. So here's a really basic conceptual overview of how AWS IAM works that I found. As you can see, AWS identity and access management is pretty complex, at least to me. And there's a lot going on between principles, policies, and evaluation and resources. AWS likes its pipelines, and I like to think of this as one big pipeline that applies to AWS accounts in various ways. The scope cloud environment we are looking at is effectively an IAM graph. So nodes are identities and resources like users, roles, and services. Edges connecting these identity-derived nodes are permissions regarding which identity and resource policies are used. And here are some examples of policies. This policy, administrator access, would provide full access to AWS services and resources per account. This one, on the other hand, provides full access to, but doesn't allow management of users and groups. This one, pass role, which I highlighted in red, assigns an identity and access management role to an AWS service. I labeled this role in red because it's easier to misconfigure due to its involvement in identity and access management. Similarly, I highlighted this one in red too because creating a new version of a managed policy leaves room for exploitability. For example, via backdoors or injection attacks, which is another example of how a policy can be misconfigured. With that, let's talk about misconfigurations. A misconfiguration occurs when a security setting or multiple security settings for user accounts, services, or roles are incorrectly defined, allowing unauthorized access, privilege escalation, or data leaks. In this example, an attacker compromises an AWS account or another cloud provider's user account. The attacker, as the user, invokes the attach user policy, which can escalate privileges because attach user policy allows a user to attach any managed policy to any IAM user, including themselves, which enables the user to escalate their privileges by attaching high privilege policies such as administrator access to their own account, thereby possibly gaining full administrative access within the AWS environment. So every attack chain like this begins as a misconfiguration, but not every misconfiguration itself becomes an attack chain. With regards to misconfigurations, they often appear to be benign in isolation, and in fact, they can be benign and harmless in certain cases. But how do we account for when these misconfigurations are chained across multiple services? For example, for an enterprise client that uses multiple tools and third-party applications like IoT, software as a service, and social media, how do we check misconfigurations that can be chained across that entire attack surface? So far, I've been speaking a lot about specifically cloud environments, but cloud identity and access management actually reminds me a lot about Active Directory and networks, and that directly inspired this tool. In 2005, if someone was interested in attack graphs, they would probably be looking to apply attack graphs into network environments. And I like to think of network attack graphs as a predecessor to cloud environments, but completely different. You can certainly compare the two different attack surfaces. The network world enumerates hosts, ports, and services through CVE exploits, connecting them to achieve lateral movement, or even privilege escalation, while in the cloud identity access management world, you would enumerate identities and roles and resources to escalate privileges through misconfigurations. Networks and the cloud, which perhaps is someone else's computer, are abstractly similar. This also isn't to claim that privilege escalation only happens in the cloud. It definitely happens in the networking world as well. But I believe that the ground truth between the two is different, where within networks, the question is, did the exploit succeed or not? Can we chain the exploits? And in cloud, did AWS authorize a policy, and can we chain that policy, misconfiguration? Attack graphs were born in the network world, and my hope with this tool is to rebuild the concept through API calls instead of software bugs. So in this tool, I am introducing this tool to help solve this ever-increasing attack surface that I am developing called PathQuarry. Here's a simplified diagram for what PathQuarry is: a system with 2 layers that takes in identity and access management roles and policies, in addition to resource configurations and trust relationships, and outputs attack paths that are prioritized and validated. The process of outputting these paths is supported by 2 layers, one of which is symbolic, while the other is a reinforcement learning layer. Within the 2 layers of PathQuarry, we answer 2 questions. Can we visualize a graph that queries resource reachability in the graph? Yes, we can, by converting the identity and access management rules into Datalog facts in the symbolic layer. Secondly, can we train a model that prioritizes different paths in the attack graph based on learned value and facts as training data? Yes, by using reinforcement learning to output optimal paths based on state, reward, and feedback in the learning layer. To show that we can answer these 2 questions, we evaluated PathQuarry on both intentionally vulnerable and public cloud environments. We then can analyze these findings by observing a visualization which takes in PathQuarry's output and graphs it into a more intuitive, human-readable format. So let's talk about that first layer. So if you remember that earlier slide of that big diagram of identity and access management within an AWS cloud environment with its policies and principles, we can see again that there are many components. But if you look closely, there are 3 main columns in the pipeline. So principles, policies and evaluation, and the resource column, all of which contribute to how specifically IAM management works. Principles describe who the users and roles are, and policies describe what they are allowed to do. An allowed decision based on a policy intersects the 2. Policy text in AWS can also look permissive in some way, but still deny access, and that's why PathQuarry validates every edge against AWS's own decision-making engine. These principles, policies, and resources contribute to the identity and access management state, which we evaluate for reachability. As a quick aside, what is Datalog? So Datalog is a declarative logic programming language that is syntactically a subset of Prolog. We use it in PathQuarry as a query language for deductive reasoning. Datalog has many different applications, but ultimately it structures itself as facts that define existing data and rules that define logic that derive new data. So here's a code block of Datalog used in molval, which is a similar network attack graph. In this code specifically, it's used to show that if P can execute code on H as owner, P would gain arbitrary access to owner's files. So you can see how existing facts derive rules that define logic within an attack graph environment. The reason why we picked Datalog is because attack graphs have recursive graph reachability, and Datalog computes transitive closure natively, so we can write the rules and it can then reach or find every possible path. The AWS IAM state that we described can be converted to Datalog facts. Identity and access management policy is typically found in a JSON file that is nested by a pretty intricate precedence algorithm. With Datalog, we want flat ground tuples. So we needed a way to flatten AWS's identity and access management policy model into facts that then let us re-implement the evaluation logic. To get into specifics, the role IAM get account authorization details returns users, roles, groups, their attached managed policies, and role trust documents in a single dump. Resource-based policies aren't in there, so you pull those per service, plus permission boundaries, and if you're modeling org guardrails, SCPs from organizations. Entity facts become unary or binary facts keyed by the ARN. Finally, statement decompositions occur when every policy statement is converted into ground facts, one per effect it expresses. These Datalog facts that we now have, we derive rules for them with Souffle. Souffle is the Datalog engine or compiler that runs the encoding, so it compiles rules into native C++ and evaluates them over the IAM fact base. So all that flattening and matching logic actually executes efficiently at scale. Reachability comes from Souffle's fixed point semantics. So the recursive reachable priv/can reach rule is evaluated to closure automatically. So Souffle computes the full transitive set of privilege positions that an identity can reach without writing any graph traversal code. Keeping this in mind, we define what we mean by transitive reachability, which is the derived legal moveset in a cloud environment. So the Datalog layer hands us a graph of every legal move, but legal doesn't mean the same as reachable. Most environments have far more reachable states than a defender can triage. So the question isn't what's reachable, it's what would an attack actually do first, or what would an attacker do first. So with this in mind, we also have our second layer, the reinforcement learning layer. We formulate escalation as a Markov decision process. A state is the agent's current privilege position, which principle it has compromised, plus the capabilities it's accumulated getting there. An action is a candidate transition, and every action is one the Datalog layer emitted and validated. So the agent can only ever propose moves that are actually legal. The reward is shaped toward high privilege terminal states, and we discount, so shorter, more direct chains earn more value than long, roundabout ones. The output is a set of converged Q values, and those give us a risk rating. So the paths that the agent reinforces fastest are the shortest way to privilege escalation. Our hypothesis is that those are also the paths that a real attacker would reach first, because attackers optimize for the path that has the least effort with the most access. So this gives us a clear prioritized ranking of which attack paths to take. So for example, in an early prototype with just 6 network nodes, our agent would move from one compromised host to servers and eventual exit through incentivized paths. The agent was given more points when optimized for the least amount of nodes needed to traverse the network while compromising the higher value targets. With these 2 systemized layers, we evaluated on several different intentionally vulnerable environments like AWS Goat and Cloud Goat, which are open source AWS environments intended for practicing hacking cloud environments. So this almost serves as a check for, is this actually working as we intended it to? We also pointed it at a real UK government repo from the Ministry of Justice, since we were looking for a public-facing data repository. It had 95 independent cloud environments, so 95 separate cloud environments, to be clear. And it automatically found which handful actually put data at risk, and it drew the attacker's path to it. So these are our results for AWS Goat, which is an intentionally vulnerable infrastructure on AWS designed to simulate real-world cloud security flaws. So it already has an existing attack chain. So we ran PathQuarry on it to find 145 facts, where our tool reconstructed that attack chain successfully with party QL injection and exfiltrated a database. So it's there at the bottom. So for CloudGoat, which is another intentionally vulnerable AWS environment, we evaluated it to about double the facts with 284 facts. In CloudGoat, 4 of 5 attack chains were proven end-to-end, including 2 IAM privilege escalation paths and 2 secrets exploitation paths. The 5th, an RCE to metadata service credential theft, is our one known gap, which is the same missing network hop you see flagged, that you would see flagged in a live scan. On known vulnerable benchmarks, the tool rederives the documented attack paths automatically. AWS GOAT was fully proven top to bottom, and in CloudGoat, 4 of 5 attack chains were proven top to bottom. But we wanted to run this on a public repository of multiple environments, so we essentially performed this scan many times on the UK Ministry of Justice environments. So to be clear again, this is as if we did multiple scans of those AWS GOAT, CloudGoat style intentionally vulnerable environments, but they're actually real environments used publicly. So we compiled the results in a PathQuarry script, and these environments are showing us data through their signal count and step count. But it's a lot of abstract data that would benefit from visualizing exactly where we can find exploitable paths, and also a heat map. So here's what the tool looks like visually. So in our visualization in HTML, when we hit play, we get this graph that shows us different paths throughout the environments that connect through misconfigurations. So the important thing to note here is that a missing edge or gap in the graph, which tells us where exactly the misconfigurations are, because something in the policies doesn't align, so there's room for exploitability. So you'd be looking at the dotted red lines, in which case the attacker is missing a gap, and so, or the policies are missing a gap, in which case those can be exploited. So in this subsequent heat map, each environment was sorted through prioritized risk. So this is the top environments. There's more at the bottom because there's 95 of them. So sorted by overall signal. So the higher the signal means, the more it should be prioritized. So if you or someone you know has access to cloud environments, we want to validate this on real data to achieve a better evaluation and help secure more cloud environments by finding their misconfigurations. If you have these cloud identity and access management problems, we would love to chat. Please come talk to me, and together we can secure more of our applications that run on cloud environments. Thank you.
Has any of this been open sourced in a way that we can run it ourselves?
So we were planning on releasing it as an open source tool, but we've made it closed source. So it's closed source, and then open source, and then closed source again. So I'm sorry about that. But one day we'll open source. I believe it.
Are you planning on targeting GCP and Azure as well, or is it just AWS for now?
Yeah, definitely. So the nice thing about Datalog is that it is very good for cloud environments, and we hope to achieve a universal kind of PathQuarry language for this. So that's ultimately the goal, yes.
So I had a question about Moolwell. What's the data that you provided to Moolwell?
What's the data I was provided to do this?
Yeah.
So the UK Ministry of Justice was one of the only public repositories we found with public available data within cloud environments, so that's what we used for public-facing data.
I also had a follow-up. Could this potentially be used to look at predictability of attacks?
Yeah, that's ultimately the goal. Is like if you can see like so there's the risk rating with the heat map, and the higher numbers, so the signal column, essentially means you should probably prioritize this because this has the most misconfigurations, or these misconfigurations are the most exploitable. So I think that's what you would prioritize and predict.
Yeah, makes sense. Thanks.
Differs from commercial products that are already on the market, like these or
So I think I think that something that we do that's different is like we do use Datalog, which I think is kind of, I don't think it's like that niche, but it's a little bit niche, and I think it has like its unique language capabilities that let us use deductive reasoning. So in combination with that, which is symbolic by itself, and with reinforcement learning, I think the two systems combined is something that we do differently and compared to commercial products.